Hello, my name is Adam Moody. I work at Lawrence Livermore National Laboratory. Very honored to get to talk at this year's HPC Knowledge Meeting. I realize this is in Barcelona, Spain, and that some people are lucky enough to get to attend in person. So I'm very jealous. I'm reporting from my home office in Livermore instead. Nevertheless, very glad that the organizing committee selected my proposal to talk and that I have an audience to listen to what I have to say. So thank you. So at Livermore, I work within the Livermore Computing Center, where we host some of the world's fastest supercomputers with some of the world's fastest parallel file systems. I'm a support staff member there, so I help users run on those machines, but I'm also a user of the machines for my own work. Today I'd like to talk about mpiFileUtils, which is an open source project we started along with Los Alamos National Lab, Oak Ridge National Lab, and Data Direct Networks to help people manage their large data sets on these clusters. So let me motivate things with an example. Imagine you have a directory with 200,000 files. Each file is 128 megabytes. It's a total of 24 terabytes of disk space. This might represent a checkpoint from a large-scale application. Now what you'd like to do is make a recursive copy of that directory. Maybe you want to modify the file somehow, but you don't want to mess with the originals. You just want to make a copy of the original directory. So the natural way to do that is just use the cp command. So I did that just about a year ago. I set up a data set, and in the morning I kicked off a copy command and let it churn in the background as I did my work through the day. By the end of the day, I was ready to go home and hadn't finished, but I was able to see how far along it got. And I could see that it had finished 114,000 files out of the 200,000 it needed to do in the 8 hours it had been running. Right? So it wasn't done, but it's close enough that you can start to make a good estimate that maybe in another, or total of 14 hours, it would have actually completed. So that's one approach. Approach 2 is to use dcp. dcp is a parallel copy tool that's part of the mpiFileUtils suite. It's an MPI-based tool. So you have to allocate some nodes. In this case, I allocated 8 nodes. And once I got those nodes, I kick off an MPI run. In this case, I use 320 processes. And let this run. It finishes in 380 seconds. All right, so what do we learn? So to summarize, dcp is just a little bit faster than cp. Right, the cp command would have taken 14 hours. dcp finished in 6 minutes. It's 140 times faster. Think about that though. What used to take you 14 hours, you can now do in 6 minutes. Right, 14 hours means on Monday, you start the copy, and when you come into work on Tuesday, now you can get to work. It takes you a whole day before that copy's finished, a whole work day. dcp is just a few minutes. You can get to work on the same day. Right, so it's a huge difference. Yeah, so what's going on here? We've got people running on these giant clusters with these fast parallel file systems. They might be using thousands of nodes, tens of thousands of processes to generate a data set. And then they try to do management with a single process on a single node. Right? They're using the cp command or the rm command. And it's just this problem of 10,000 to 1 scale. It just doesn't work. Right? It's a bad idea. So mpiFileUtils is designed to solve that by using the same resources to manage the data set that you used to generate it in the first place. So these run as MPI jobs on the same compute resources using the same nodes and the same network and the same file system. They're designed to be able to scale up so you can throw more nodes and processes at the problem if you needed. And they're designed to run across all the common parallel file systems you deal with in HPC. So what is mpiFileUtils? Well, it's actually 3 things from a high level. It's a library, a suite of tools, and a file format. So the library portion. We try to bury a bunch of common functionality that's useful to a number of different tools into this common library. The goal of that is to make it easier to write new tools, or even for applications to use mpiFileUtils directly. In addition to the library, we distribute a set of pre-built tools. And these are MPI-based replacements for commands like cp, rm, ls. things you need to do sort of day-to-day data management tasks. And then there's a file format, which is common. The library supports reading and writing this common file format, which makes it easy for tools to interoperate. So the output of one tool can be used as input as another. It's actually a very important aspect, and I'll get into that more later in the talk. So let me give you a little bit of background on the project. And around 2013, I decided I really want to help build a suite of tools like this that people could use. I'd seen enough people struggle to realize we really need to get a solution here. So I started looking around to see what was available already. I figured I'll start from something that already exists if possible. And the one that really caught my eye was DCP and libcircle, which was software written by the same group of people at Los Alamos. So I reached out to that team and I said, would you be interested in working with me in building out this suite of tools? And they said, yeah, sure, we'd be on board. And in fact, we know people at Oak Ridge and DDN who might also be interested. And so we started off this project as this team of 4 institutions working on this back in 2013. The magic of libcircle was that it was a way to distribute work across a set of processes without using the traditional sort of manager-worker approach that a lot of other projects used. The problem with the manager-worker approach is that there's this inherent bottleneck, a scalability bottleneck at the manager process. So that eventually you scale big enough and it just doesn't perform that well. In libcircle, all the processes are sort of symmetric in their behavior. So every process has this local work queue. It pulls items from its local queue. It might generate new items and insert them to its local queue. If it ever runs out of items, it just randomly asks some other process for work and steals some, if there's any taken. Right? So it's a natural way to sort of diffuse work across a set of processes. Then they built DCP on top of that, where they implemented all the functionality you need to do a copy on top of libcircle. From walking the source directory to doing the file creation for the destination, actually doing the data copy for the destination files, and then finally doing the metadata updates on the files. All of this was happening asynchronously. We changed that as we got mpiFileUtils going, but this served as the basis for the project. So now with that background, let me dive a little bit into the common library libmfu. The most central concept in the common library is what we call the file list, or the mfu list. This is a distributed list across the set of processes where each process has a subset of the global list, each element being the stat-like information for an item on the file system. One of the ways you can generate this is given a path, you can walk that path recursively with libcircle, where every process stats the files that it's responsible for. Right, and so in that case, you end up with each processing owning a random set of items under this directory tree. So then we define a number of different functions that operate on an flist. Some of them are collective across the whole set of processes. Some of them are local to the process. On this slide, I'm showing some of the most frequently used functions. I've colored the collectives in purple and the local functions in green. Right, so just to give you a sample of this, a walk I've already talked about. This is with libcircle where you generate the list. Stat is another way to generate a list where just given a set of file names, you go out and stat them all. You can filter a list, so giving an initial list, you apply a filter to it and end up with a subset. Depth is a way to split an initial list into sublists, depending on the depth of each item within the file system. Remap and spread are ways to reassign elements to different processes. The same with a sort. Copy, makedir, and make node are used when you're trying to copy a source directory into a destination location. Unlink is a way to remove a set of files or items from the file system. Read and write. So these are important. This is getting into that common file format I was describing. These are the functions that will read a file list from a file back in or write one out to a file. And then all these items in green are the local operations. Basically, it's a way for the process to query the information that's local in its subset of the global list. give you a flavor of these functions, here I'm showing the sort operation. So on the left side is a list that might have been generated after a libcircle walk, where each process ends up with a random set of items under a directory tree. All the processes then call this mfu flist sort. In this case, they're sorting by name, which sorts by path. And after the return from that, they end up with a list on the right where the items have been globally reordered across the processes so that the items are now in alphabetical order by path name. So now that you understand that, you've actually seen enough to write your own tool. This is the example tool. This is a real case where somebody just recently asked for something that does exactly this, where they wanted to walk an initial path, then pick out all of the regular files that had more than one hard link, and then save that list to a file. And so this is what this does. I realize there's a lot of text here, but it's not that complicated. I'll just walk you through it. I've colored, again, all the collectives to be purple and all the local functions to be green. On the right column in blue, I'm showing some comments of what the code does. But these first few lines just allocate an empty list and then walk a path to generate the initial list to work from. In the middle portion, we then create a second list, which is going to be a subset of that initial list. And in the for loop, each process runs over its local items of the list. It first identifies whether the item is a regular file or not. If not, it moves on to the next item. If it is a regular file, it stats the item again to get the hard link count. Turns out that the hard link count is not one of the properties that we're currently saving in our stat information. So you have to stat the item one more time. You stat the item. If the hard link count is greater than 1, then it copies the item from the initial list into the subset list. And then finally, when each process is done with its for loop, we call a summarize. The summarize is a collective across a set of processes that computes global information about the list. For example, the total count of items in the global list. We then write the list of hard link items out to a file and then free off the list. Right? And this is basically what every tool looks like. In the production tools, we might have some more code that does option processing and error handling, but this is sort of what the guts are of every tool. So let me take a few minutes now to talk about the tools that we distribute with mpiFileUtils. This list is showing the set of tools in the current release, version 0.10. We break these tools down into two sets, production tools and experimental tools. The experimental tools are not really meant for end users, but they're useful for developers as further example tools that you might work from. In some cases, they're intended to be eventual production tools, but they're not quite ready yet. I've colored the production tools in black and the experimental in red on this chart. Let me run through the production tools just to give you a quick summary of those. So dbcast. This is useful for broadcasting a file from the parallel file system out to all the compute nodes. For example, if you want to load a tarball from the parallel file system, say onto the SSD of every compute node, this is a good way to do it. It runs so that it only reads the data from the parallel file system once, and then uses MPI to broadcast the data between nodes. dbz2 is a parallel compression tool. dchmod is kind of like a combined changemod change group. It allows you to change the permission bits, the owner ID, and the group ID on a set of files in parallel. dcmp is a parallel compare tool. It's useful for comparing the bytes between files of a source and destination directory to identify whether you have an identical copy or not. dcp is a parallel copy tool that you've seen already. dedupe is a way to find files within a directory tree that have identical content. It's a very interesting algorithm. dFileMaker is mainly just used to generate test sets. So it's not maybe all that useful for end users. dfind is a parallel find tool. drelink is a way to update symlinks. For example, after a large recursive copy, if the destination directory contains symlinks with absolute paths that need to be changed, it's an efficient way to do that. DRM is a parallel remove. dstripe is a way to restripe files on a Lustre file system to have different striping parameters. Desync is like a parallel rsync. It's mainly used to synchronize a source and destination directory to make sure they have identical contents. Unlike rsync, it doesn't run across an internet connection. It's really only intended for a case where the file system is mounted or multiple file systems are mounted on the same cluster. And then finally, dwalk is a way to summarize a directory to see sort of what contents are there. And it's also useful for sorting data in various ways. In the next portion of the talk, I wanted to demonstrate the scalability of some of the tools. So I want to use a test set. I'm using our familiar test set of a single directory, 200,000 files, 128 megabytes of file, so 24 terabytes in total. And we're going to use 4 different tools to do different operations on that. First, we'll use dcp to make a copy of the dataset. After the copy, we use dcompare to compare the contents between the source and destination directory. Then we use dchmod to change the group on all the destination files. And finally, remove the destination copy with drm. We'll do this on the Sierra cluster at Livermore, and we'll scale up the node count from 1 node up to 1,024 nodes. So here I'm showing the DCP cost to copy that data set on Sierra as we scale up the node count from 1 to 1,024 nodes. The cost is shown in seconds on the y-axis. So recall the original DCP from the Los Alamos work was built entirely on libcircle. All phases of the copy operation were done as libcircle operations, from walking the source directory to creating the destination directories and inodes, to copying data, and then finally updating the metadata on the files in the destination. That's one of the things we changed when we rewrote DCP and mpiFileUtils. So we now separate those out into distinct phases. First the walk on the source, then creating all the destination items, then doing the copy, then doing the update. In fact, the only piece we're currently using libcircle for is the walk itself. Right? So we lose some because we're not overlapping operations as much. So it could actually run slower in some cases. But what we gain by doing that is that by moving each of these into its separate collective, it makes it reusable by more tools. It's easier to reuse those operations. The other side benefit from it is that you can time each of those independently, and which is what I'm doing here. So I'm showing each of those phases is a stacked bar graph. And finally, there's an other column here where I surround the tool with a time command to account for other time that we're not timing within the tool itself. This often is due to the system just launching the MPI job. So maybe the resource manager or MPI bootstrapping, or just the cost to get the libraries out to the compute nodes. So you can see here the scalability is very good. Most of the cost is in the actual data movement itself, the copy component. And that declines nicely as you scale up the node count, where it sort of saturates the file system around 32 nodes. The other thing I did is I ran a standard CP command. And it's not shown on the graph, but I ran this as a compute node job, and so it didn't get interrupted this time. I didn't have to kill it. It also wasn't competing with other processes on the login node. In this case, it was able to finish that copy in 12 hours and 45 minutes. If you recall, before our estimate was around 14 hours, right? So it did a little bit better than that. If you look at the chart, the minimum DCP time happens at 64 nodes. You can't read it from here, but it's 93 seconds. Right? So that's a speed up of almost 500 times. Right? So what used to take you 13 hours, you can now finish in 2 minutes. So again, showing the power of mpiFileUtils here. It's interesting to dive into the DCP results in just a little more detail. For example, one of the things we can do is plot the effective bandwidth of the tool. Here what I'm doing is I'm taking the total dataset size of 24 terabytes and dividing just by the copy portion, which is the gray portion from that previous stacked bar graph, to come up with an effective bandwidth for the data movement piece. I ended up doing 2 runs, So I'm showing one run in blue and one in orange. But for the most part, they're the same. And as you can see, the bandwidth scales up nicely until you saturate at 320 gigabytes a second around 64 nodes. It's also nice that it doesn't decline too much as you continue to scale higher. Right? The file system is still delivering that high bandwidth with higher process counts. Though in practice, you're not going to get the job done really any faster with higher node counts because you've already saturated the bandwidth. So once you hit the top of that peak, there's really no value in running the tool on more nodes. Moving on to the dcompare tool. So again, we use dcompare to compare the source directory to the destination directory to verify that all the bytes are the same across all the files. So this is actually reading in the bytes from all the source files and the corresponding bytes for all the destination files and doing a comparison byte-wise. So it's a very read-heavy operation. It's recommended to run this tool after you do a DCP just to verify that the contents are correct. Anyway, we can produce a similar kind of chart that we did with DCP, and you see a very similar behavior with dcmp. Just as we did with DCP, where we computed an effective write bandwidth, you can compute an effective read bandwidth with dcompare, which is what I'm showing here. And again, we're seeing very good scalability. In fact, saturating the read bandwidth on the parallel file system at 1 terabyte a second on Sierra. So getting very good performance. Now let's move on to take a look at dchmod to change the group on the destination items. Unlike dcopy or dcompare, which are bandwidth heavy, dchmod stresses the metadata operations. I actually ran this test on both Sierra and Quartz, two different machines at Livermore. Each cluster has a different backing parallel file system, a different MPI library, and a different job launcher. And you can see those differences in the results. In both cases, this operation finishes quickly, and so it makes sense in those cases to use a small node count. Right? On Sierra, you get some improvement going from 1 node to 2, but really the maximum performance is at 2 nodes. Beyond that, the cost of just starting up the MPI job starts to dominate. On Quartz, the scalability is a little better. You can maybe stop at 8 or 16 nodes, but you're not improving much beyond that. So the takeaway here is that fast-running jobs can get by with smaller node counts. Then finally, let's look at the performance of dremove to delete the copy at the end of the test. This is a metadata-heavy operation, and the results look similar to what we saw with dchmod. Again, I ran this test on Sierra and Quartz. I think what's interesting in this case is you can see on Sierra, the cost to remove items decreases as you increase the node count up to 128 nodes, but then it starts to get slower again. Right? So that's not scaling well. We don't know the reason for that. It's not clear whether it's inside the mpiFileUtils or something in the file system itself. Maybe we're thrashing the servers in some weird way. But the point is, this is something you might want to look out for, that you can end up with these sweet spots and that increasing the node count doesn't always give you the best performance. It's not desirable, but just keep an eye out for it. Now, one thing to remember is that these tools are MPI programs, and so there's certain implications because of that. For one, you typically need to run them inside of a compute node allocation. Right? Usually 2 to 4 nodes is enough for most things. If you've got large data sets, you need to grab more nodes than that, though. Also, you have to launch the job with MPI run, or its equivalent. And then when launching a job, I usually try to maximize the cores that are being used. Except that you'd like to leave a few free on every compute node for the file system. The file system has to run processes usually on the compute node, and you don't want to starve those processes out. The tools do not checkpoint themselves, or at least most don't. And so it's important to request enough time on your compute allocation so that the job can finish. In some cases, if the job gets interrupted, you have to start over from the beginning. Also, the tools cannot pipe data from one tool to another, like you might do with standard Linux commands. But we have input-output options that play a nice substitute for that, and I'll show examples of that later. That comes back to the common file format. And then also, you can't really check the return code of the tool to know whether it succeeded or not. That's not really defined well in the MPI standard. Instead, you have to look at the output from the tool and sort of scan it for errors. Let me finish up the talk here going over a few of the most frequently used commands. The first thing I want to mention is that most of the tools operate in singleton mode. And if you're not familiar with what that is, MPI lets you run a job without an MPI run statement, in which case the application just runs a single task MPI job. Not all MPI libraries or all machines support that, but if your machine does, it's a very handy way just to get like the help output from a tool. Or if you're working with a very small data set, you can just run it as a singleton. Right, so here, if just running dwalk help will give you that output. The rest of the examples I give in this section are sort of all running as singleton modes. You wouldn't always want to run them as singleton, but it just saves some keystrokes on the slides here. Okay, so one of the most useful commands is dwalk. Dwalk is sort of like a du in that it gives you a summary of a directory. So it'll tell you how many items you have and how much data is there, including a breakdown of directory and file count. So it's a good way to scan a target data set that you want to do something else with to judge at how many processes you might want to throw at that problem. Right, so you just do the walk and it gives you the summary. Because the walk can be expensive, one of the things you can do is you can have dwalk output that flist to a file. And then you can read that back in later using an input option. So you walk the path, give an output option, it saves the information to the output file. And then if later you want to come back, you can read that list back in, right? And so that's a snapshot of the file system in time. It might not account for any changes that have happened since you wrote the output file. But you can read that in far faster than you can walk the file system again. The file format that mpiFileUtils writes out to is really just meant for mpiFileUtils. It's not meant for human consumption. It's a binary format. It's possible to write a list in text format that's easier to read as a human. You can throw the --text option on there to do that. However, that format's lossy. You can't read the text format back in to mpiFileUtils because it doesn't contain all of the information that should be there. There are times where you might want both. You want a binary format and a text copy of it. In that case, what you can do is you can write to the binary file first. You do the walk, output to a binary file. And then use dwalk to read that file back in and output a text file. So another useful feature of dwalk is it can sort. You can sort a list in different ways, a number of different fields, both ascending and descending, and you can use them in combination. So remember, after you walk a path, you end up with a random set of items on each task. And you may want to output that list in some sorted order. So in the top, I'm showing how you sort a list first by username, and then by access time, and then save that to a file. The bottom example does a sort by descending size. So biggest items first. Three other tools that are really useful: dfind, dchmod, and dremove. So find is a way that you can filter a list. So given an initial list, you can find a subset of items that meet some Boolean expression and then save that to a subset list. Currently, the Boolean expressions are limited to AND conditions, but it's on our to-do list to support more expressive Boolean conditions in the future. Right? So for example, if you want to take an initial list and find all the files owned by a particular user that are bigger than 100 gigabytes, this is a command you might use. dchmod, like I said earlier, is sort of a combination of a change mod and a change group all in one. Right? So it lets you change permission bits and owner and group IDs on files within a directory tree. And DRM is effectively like a remove-rf, but a parallel version of it. And then let me end up here with dbcast and dsync. So dbcast, as I said before, is a way to broadcast a file from the parallel file system out to all of the compute nodes. It does that by only reading the data from the parallel file system once, and then the compute nodes share the data through MPI. It's one of the few tools that you actually have to run with at least 2 processes per node. Most of the tools don't have that restriction, but dbcast does. And then desync is a way to synchronize a source and destination directory. It's actually the way that I recommend people do copies. But it synchronizes the source and destination in that it will copy new files in the source over to the destination as needed. It can also delete files from the destination if they've been deleted from the source. So it's sort of like rsync, but a parallel version of that within the cluster. One of the reasons I like to use this to do copies is that it has a nice batch files option. So you can specify the number of files you want to operate on, and then it will copy that many files at a time and sort of complete each batch. And so if it gets interrupted, it can pick up from its most recently complete batch. So it's sort of like a built-in checkpointing mechanism. One last example I'd like to give here is how you can use these input-output options in this common file format to chain tools together to interoperate. Right, so one example of that is consider that what you want to do is find all the files on your file system that haven't been accessed in the last 180 days and then delete them. Sort of like a purge operation, right? You can combine dwalk, dfind, and drm to do that operation using these input-output options. So you can have dwalk walk the file system and save that to a file. You can then use that list as input to dfind, and then have dfind pick out all of the regular files whose access time is 180 days or longer, and then save that subset to a purge list. And then finally give that purge list as an input list to drm. That will accomplish the purge. Now, wrapping up the talk here, one of the design goals for mpiFileUtils from the beginning has been that we'd like this to be available basically at every HPC center you might come across. So the tools are designed, they're actually written in very basic C, MPI, and POSIX libc calls. There's nothing fancy about that. There's a few dependencies that you need, but not too many. At a number of HPC sites, the support staff has installed them already for you, so they might already be on the machine. And if not, they're easy to build as an end user. If you're using SPAC, it's a single line to install. Otherwise, you can run through the cmake command yourself after you install a couple of dependencies. So we're trying to make it easy to install and so that it can build on all the different HPC centers. We're also wanting it to work with all the common file systems that you'll come across, right? So from the beginning, Lustre, GPFS, NFS have been targets. We're also now working with Intel to incorporate DAOs. The default algorithms in the tools are all POSIX compliant, so it pretty much should work on any file system you come across. We then try to optimize those where possible to put in file system specific optimizations. Okay, and then finally, let me end with this page. I've got URLs here to our documentation and our source code. Of course, we're happy to have new users and feedback about the tools and bug reports. We're even happier to have new developers if you're interested. It is an open source project and the team's very welcoming to new members. We could certainly use the help if you're inspired to help us build this out further. From the beginning, we've had a large number of people contribute over the years. People have come and gone. We're trying to keep track of that in a couple of different locations here. I've listed URLs to the authors and contributors on GitHub. The main takeaway message, I guess you can go away with, is there's the standard Linux commands, copy, ls, remove. And if those are working fine for you, please just keep using those. If you're working with datasets that are large enough that those are starting to feel slow, then it's worth taking a look at mpiFileUtils. And with that, I'd like to thank you very much for your time and attention and listening to my talk. Happy to take questions. Thanks.